So welcome everybody to our Gamma seminar. Today we have the pleasure to get Tomasz Sobczak, who is going to talk about K-contactless systems. So Tomasz, thank you for accepting our invitation. The floor is yours. Go ahead.
Okay, so thank you for the introduction and the possibility to say something about what the title suggests, the K-contactless system. And the title might be similar because I already talked about a little bit about the K-contactless systems. However, there will be things that will appear once again, but there will be also new things that we added and made, I believe, more interesting to it. Because previously we have only one way to construct the K-contactless systems, and now I will show the method how to obtain it in another manner, more interesting one, I believe. So as an outline of my talk, I will once again introduce really briefly, because as I said, I talked about it previously. So just this short introduction to Lie systems, the elements of K-contact geometry and eta Hamiltonians, precisely the useful ones, meaning because there are a lot of things to say about the K-contact geometry, and there's many things how we can use it. However, I will proceed and recall the most important ones, and I will glue together those notions to present the K-contactless systems. And as I said before, I will show the new way to construct the K-contactless systems more with the richer structure. And as a bonus, which didn't appear previously and is a relative new thing, I will say a few things about the PDE systems, so the partial differential equations that also will have some superposition rule, and how we can apply the K-contact geometry to it. So as an introduction, I want you once again to consider a differential equation of this following form, meaning that we are proceeding on R, just R, and the differential of x with respect to the parameter t is just the function of b1, b2, and b3 multiplied with respect to 0 first and second power of our x. And those functions can be arbitrary, they're time-dependent, and it is well known that if we know 3 particular solutions to a given problem, then we can recreate the general solutions via these functions. So as we can see, we have x1, x2, x3, and we can generate all possible solutions via this function. And this property...
Sorry, Thomas, there is little nuance about what you said. And in reality, you can, when you have 3 fixed different particular solutions and you restrict K to be a real number, you recover almost every solution. Indeed, you will not be able to recover, for example, x2t. Okay, so it's
yes, I wanted to say later,
okay.
Because in the definition I will use the global term and then the local, and then I wanted to say exactly on this example what is the difference.
So let me just say another thing. It is that you didn't say. I know maybe you know, but it is maybe interesting. Normally, when we describe these things, we have a little our terminology, and it's a little bit different from what you can find in other papers. For example, the differential equations number 1, we call them Riccati equations, but in the literature, sometimes there are some additional conditions on the time-dependent coefficients. Normally, it is said that, well, sometimes that b1t times b3t must be different from 0, yeah? So it's a little bit different, yeah. But in order to avoid all these stuff mutations, normally we call them just Riccati equations. Thank you, and I'll let you to go on. Sorry, Thomas.
Yeah, it was really important detail, but maybe I made a little bit shortcut. But yes, this is the additional thing. But just for clarity, I present the main idea that we have an differential equation of this form, and we can express the general solution, or at least almost all solutions who are equation via the particular solutions, what we found.
Yes.
And exactly, we can see that we can do it using such a function. I will call this function the superposition rule. So just to have a definition in mind, we can say that the system of first order ordinary differential equations on M it says that have global superposition rule, and this is this difference I will talk about a little bit further between the global and the local superposition rule, meaning in this case we can recreate all possible general solutions via the time of t independent map, which takes our M particular solution and some constant or element of M and generates all possible solutions. And once again, there's this this family of particular solutions has to be a generic family of particular solutions. I don't want to go into details, just they are more technically, but as an idea is just we have M particular solutions, element of M or just the constants, and we can recreate a general solution for our initial problem. And if we define the superposition rule in such a way, we can say that the Lie system is just the system of first order ordinary differential equations, which admits a local superposition rule. And there is this difference between local and global, meaning in local case, we can recreate only almost all solutions, not all. For example, if we go, I don't have to go back because as an example, I will give once again, the Riccati equations admits the superposition rule, what we gave. And as Javier said, if we limit ourselves only to the R, we cannot get for example, x2. We cannot recreate via this via these functions this particular x2 solution. So it's not a global superposition rule, but if we, for example, take R with infinity or just if we take it, we can say about the global superposition rule. If we limit ourselves only to R, then we have local. So this is the nuance, but yeah, this is the difference between those two things. And now one can ask, okay, so we know that we have some partial differential equations with the superposition rules, and how can we identify them? Meaning, how we can find out if our system is a Lie system. So to do so, I will just introduce, I will make a remark about our systems, meaning if we have a first order ordinary system of differential equations in normal form, we can relate it to a time-dependent vector field in such a manner. And once again, it was said previously, I invite to about the time-dependent vector fields, or later in my talk will be appear the what is a k-vector field. Everything was talked about in detail before, so if there is any doubts, I recommend to check it out. But in basically the time-dependent vector field, if we can represent it as a sum of the coefficients, which is just smooth functions that dependent on time of and x, and the partial differential of xi, is related to a system of our first order ordinary system of differential equations such a manner. Meaning we can relate them and we can exchange them. We can think them as the same thing, basically. Meaning, for example, if we take the Riccati equation, we can see that it describes the integral curves of the time-dependent vector field of such a manner. And the additional thing that can be noticed is that we can these decompositions, as we can see, can be done using free linear combination of three vector fields only on R without the time-dependent part, meaning x1, x2, and x3. And additionally, we can see that they are close undertaking the commutations, and the commutation relations are exactly what that are given. And as a bonus, we can see that this is a three-dimensional Lie algebra, which is additionally isomorphic to SL2R. And it occurs that these conditions, meaning that we have the composition and the vector fields included in this decomposition spans the finite-dimensional Lie algebra is sufficient to say that our system is a Lie system. And it is obtained by the Lie-Scheffer's theorem, which says that if we have a system X and it admits a superposition rule, it means that its associated time-dependent vector field can be cast exactly in this form that we can like separate the time-dependent and the manifold-dependent part, and we can write it in such a manner. And as we can see, the arbitrary time-dependent functions are dependent only on t, and those vector fields that depends only on the point x spans the r-dimensional real Lie algebra. And this Lie algebra has its own name specific. It's called the Weiswott-Goldberg Lie algebra. And I believe it's more worth noting that this decomposition is not unique, meaning we can decompose it in another manner and we'll obtain the different superposition rule, but it will still work. So this decomposition is not, so we can have a few Weiswott-Goldberg Lie algebra associated with the one system. And the terminology that will be useful, I will introduce. What does it mean that we have a locally automorphic Lie systems? Is that if we have a Lie systems on a manifold M with Weiswott-Goldberg Lie algebra, and additionally its dimensions coincides, meaning that we can span the tangent space of our manifold using this Weiswott-Goldberg Lie algebra, then we say that this system is locally automorphic. And this will be very useful while constructing the K-contact Lie systems. We did it before, but this is the method. The next method also uses it. So this is important stuff, and we will use it later. So I wanted to underline what is automorphic Lie system. Okay, so I finished my introduction. I believe everybody knows what is the Lie systems for now. And now what we want to do is analyze those Lie systems via the K-contact geometry, which Javier and I was talking like a month ago or something. So I want to recall what is the K-contact geometry and some properties and the main theorem that I believe wasn't mentioned before, or wasn't underlined enough, but we'll heavily use it to construct the new to do the new method of obtaining K-contact Lie systems. So as a beginning, once again, we generalize the structures, the contact geometry to the K-contact realm. So instead of have one form, we'll have now the differential K form, for technical reasons defined on some open subset of our manifold, and it has to fulfill some three conditions, namely its kernel of our differential K form has to be regular non-zero distribution of current K. This non-zero is just the technicality that excludes some degenerate examples. So it's a nuance, but very important one. The kernel of the differential of eta, which is also the subset of TU, has to be regular distribution of rank K. And the most important one, the important property as in the end is that those two kernels does not intersect. So this intersection with kernel eta and kernel d eta is equal 0. And you want some terminology that if we have because previously in literature, most people was dealing with the globally defined K-contact form. So we gave it a proper name. We will call the co-oriented K-contact manifold such a manifold that has a globally defined K-contact form. And this is so. Additionally, we can name the distribution, namely the kernel of the eta. We can say because it will be called a Reeb distribution, which I will say what is a Reeb vector in a minute, and its leaves can be said that are Reeb leaves. I'm not sure we'll use much more of this terminology, but that that we have a Reeb distribution will be important, and that we have a Reeb vector fields will be also very, very important.
Yes, a comment, Thomas, about the non-zero distribution. The key point to explain that is that you want a one contact form to recover a contact form. Yeah. So
yeah.
the problem is that on a one-dimensional manifold, for example, R, eta equals to dx normally satisfies all the axioms written in there, apart from the fact that its kernel is non-zero. So if you don't exclude the case that the distribution, the kernel of eta must be non-zero, the one contact form could be d eta on R, okay? And that's not a contact manifold. So the thing is, to avoid that one contact form reproduce exactly what a contact manifold is, you have to explicitly eliminate the possibility of having the kernel of eta equal to 0. So it's just a technical issue. It's just to ensure that you are not going, you can see that one contact form is always a contact form, yeah, and exclude this particular case. There are some nuances and technical mistakes in the literature related to it, but although it's wrong, it's not a big deal. It does not produce any very bad result or things like that. It's just a technicality. But the thing is, the non-zero distribution allows you to say that a one contact form is always a contact form. This is the idea.
Yeah, of course. This is what I meant, that these conditions excludes the degenerate examples, but yeah, this maybe well better said that it's just for ensure that we recreate a contact form with if k is equal to 1. So thank you for the comment. And yeah, so if we have a co-oriented k-contact manifold, then we can prove that there exists a unique family of k vector fields that fulfills such a condition. So they are really nice because they span the kernel of the eta, because each one of them is 0 on each d eta. And contracted with eta itself, it gives us 1. So they span the image of the eta, each one of them. So and additionally, they commute with each other, which will be very useful, and we'll be using them for ensuring the how to find the k-contact distribution. And this is exactly what I wanted to say, because the k-contact form, as you can see, the analysis of the k-contact geometry in the literature was focusing in the k-contact form. And to find, for example, for the Lie systems, as we want to do here, it's not an easy task to find the proper k-contact form that fulfills all those properties and is compatible with our vector fields related to Lie systems. So the better thing to do, and much easier one, is to go through the k-contact distribution way. And to do so, I will introduce what does it mean for the to be a k-contact distribution. And what is importantly, I want to do so without referring for any specific k-tone contact form. I mean, I want to know what is the k-contact distribution without referring that is, for example, the kernel of the k-contact form. So to do so, I want to say, for example, if we can start what is a k-contact distribution, we can say that it's just the distribution as a subset of our tangent space of a given manifold M, such that for every point x, we can find the open neighborhood of our x that our distribution is a kernel of the k-contact form. And we can say that this pair MD is a k-contact manifold, not co-oriented one, because now we don't require our eta to be globally defined. So this is also the useful notion, because we don't have always the globally defined eta, but we can have still a k-contact manifold just without globally defined k-contact form. And as a really nice example is, I believe I gave it in the previous talk, is just the first order jet bundle with such coordinates, because we can find the k-contact distributions, and it is a k-contact manifold, because we can see that we have the k-contact distribution C. It is a k-contact distribution because it's locally a kernel of k-contact form eta of such a form. One can see that this k-contact form fulfills previous properties, and the kernel of it is exactly C. However, if one can try to find is this contact form is globally defined, it will fail, meaning the it is not globally defined k-contact form. So we cannot globally define the k-contact distribution. However, locally we can say we can do it, and it makes the first order jet bundle a k-contact manifold, not co-oriented one. So you can see that this distribution approach is more general and sometimes much more useful than the k-contact form one.
This distribution is the so-called Cartan distribution, right?
Yes, exactly. I skipped it, but yes, good point. That is this our distribution is also the Cartan distribution in this case. Yeah.
Just one comment. This is a very good example of k-contact distribution, but it's a special type of k-contact distribution that meets both the properties, strong properties to be satisfied. So one shouldn't think that every k-contact distribution is of this type, okay? Because this is a so-called polarized. Yeah, maybe you. So
I just wanted to agree that there is a additional condition for polarization for our k-contact distributions, which is just additional thing that it is really useful, because it ensures that we have a Darboux coordinates on our k-contact manifold, and if we have a polarization, then we can say that this is homomorphic with C. However, yeah, this is the additional property that as I said, I believe I talked it before, and this is not useful for our case in this, so I skip it. But yes, this is a nice comment that not all. This is the polar. It should be added that this is a polarized k-contact distribution. Okay, so but this was just the example, just to grab the idea what does it mean to be a k-contact distribution. And as I said before, we want to get rid of this thinking that, okay, we have a k-contact form and now we will find the k-contact distributions. We want to the opposite, maybe not opposite, but without referring to it. And to do so, we have to introduce the notion of maximally non-integrability, as will be useful later. So I'll just because it was presented before, but I will recall that what does it mean to be maximally non-integrable. So if we have a regular distribution on M, and we define of M to the quotients of the tangent space with our distribution, then we can define a vector bundle mapping of such a form, meaning that it's defined on the distributions. It's defined on the cross product of the distributions. Which takes so it just takes two vector. It maps to the quotients of our TMD. Then we can define it as this projection, what we defined before, of the commutator of two vector fields that takes value exactly at x, meaning those vector fields are the vector fields, these vectors are the vectors in the point x. So which is written below. So if our vector fields are taking values in D in our distributions, so around every point X, they give some, around every point X, they give some vector field, vectors, and we can define this vector boundary mapping such a way. And if we want to be D is to be maximally non-integrable, we want those projections to be non-degenerate, because one can see that this is just the, so we're just taking the commutator of two vector fields that are taking values in D, and we project them on this quotient space. And if we have something non-degenerate, so there is no, so it's just no degenerate, we can say that our D is maximally non-integrable. And as a comment, I will just see that this is because one can say, okay, but there we are taking specific vectors, and there we have taking the vector field. So maybe it does depend on the coordinates. However, it is well defined as from this argument, because if we, for example, takes our D, and this is what we are interested in, meaning our D, our distribution is locally the kernel of some K of some K form, and what is important, it don't have to be K contact one. It's just any K form. Then we can trivialize these quotients just for this manner, and we can express our rho as just the contraction of our differential one form with this commutator. And if we calculate it by hand, we can see that we have those three terms, and one can see that there we have a contraction with zeta, but we say that we are taking both x and x prime from D, meaning they are the kernel of zeta. So this term vanishes, this term vanishes, and what we are left with is well-defined tensor thing that takes our two vectors in every point of X. So as you can see, though this mapping is well defined, and if we additionally say that because previously we took any differential K form, now if we take the K contact form, then we can see that our d eta, because we get the d eta, has to be non-degenerate when restricted to kernel of eta, because now kernel, so those vector fields are taken from the kernel of eta, and if we restrict our rho exactly for this d, so our d eta on this rho, it has to be non-degenerate, meaning it has to be maximally non-integrable, because we had these conditions that the kernel of eta and d eta does not intersect. So this follows from it, and we have that, in other words, eta is maximally non-integrable. And this proposition with additional definition that I will provide before, but I want to underline because we'll heavily use it from now. Meaning, additionally, if we have a distribution D on M, we can call it a least symmetry of D if we take the commutator of X with any element of Y, and we are still in D, meaning I can write it in such a manner that commutator of X and D, meaning that we are taking all elements from all vector fields that are taking values in D, it's still in D. And if this is fulfilled, we call it X and the least symmetry. And with this definition, it can be proved that the distribution D on M is a K-contact distribution if and only if it's maximally non-integrable, as before, meaning as before, and around an open neighbor of U, it admits K least symmetries S1 to Sk such that this decomposition holds, meaning around every open neighborhood U, once again, maybe the technical one, but important one, because now we are operating on the K-contact distributions, not the K-contact form, so it don't have to be globally defined. So just on the open neighborhood of U, we can decompose the tangent space of our neighborhood as this distribution, which we started restricted to U, as a direct sum with those with the space spanned by those symmetries. And these conditions additionally, and it is worth noting that those symmetries has to commute between each other. So this commutator has to be 0 for every I and j. And it was, I may be repeating myself, but I just want to underline that some technicalities or some details were covered before, but it is important to note that the maximally non-integrability of the distribution D is not enough to ensure that the that we are dealing with the k-contact distribution, meaning this additional decomposition and those additional symmetries are crucial to prove that our distribution D is a k-contact distribution. So this part will be very useful because one can see that this Lie symmetries that we'll use in the Lie system constructions, k-contact Lie system construction, will be just the Reeb vector fields. So we will do it that those symmetries will be the Reeb vector fields, and using them we can construct the k-contact distribution and then the k-contact form, which we will be interested in. So we'll just switch the perception. Before we had the k-contact form, and it gives us the k-contact distribution. Now, without referring any k-contact to any specific k-contact form, we can construct the k-contact distribution and then find its kernel. So so this was the preliminaries, I believe. And the thing that will be also important is just we want to impose some dynamics of our resistance, because now we prepared how to impose the k-contact distribution, k-contact form, and now we want to impose some dynamics related to this structure. So as a definition, we can say that if we have a k-contact vector, if we have a k-contact manifold, we can construct the k-contact vector field, which is a Lie symmetry of D, namely exactly what I said before. This is maybe the shortened version. So the commutator of X with any element of D stays in D, basically. And this is the definition of the k-contact vector field. However, if we are dealing that D is the kernel of our k-contact form, then we can say that X is the eta Hamiltonian vector field, and we'll heavily use it. So this one is just for clarity. However, this notion is very important, and we will analyze our Lie systems via the eta Hamiltonian vector fields, not the k-contact vector fields. And additionally, one can define the eta Hamiltonian Khan function in such a manner. And why is that? I will give just the proposition. And this is a more useful one because this is just the definition that this proposition gives us just the properties that has to be fulfilled for our eta Hamiltonian K function and eta Hamiltonian vector field to be fulfilled. So if we have a eta Hamiltonian vector field and eta Hamiltonian K functions, it has to be fulfilled that the contraction of X with each eta alpha gives us a minus H alpha, and contraction with each d eta alpha of our eta Hamiltonian vector field has to be equal to the differential of our function, of our part of our eta K function H, minus, and there, I believe, I'm not sure because it was changed, but now there is a little bit change. Before, I believe it was only one term, only that the Reeb vector field was acting only on H alpha, and now this definition is more useful. We'll sum over all Reeb vector fields will act on the H alpha, on the specific element of our H, and multiplied by corresponding element of our k-contact form. So I believe there was a change in previous definition, so it's worth to emphasize it. However, the rest is the same, and this proposition is very useful because now we have specific conditions to fulfill if we want to have a eta Hamiltonian vector field, it has to fulfill this proposition, and we will use it to construct the k-contact Lie systems. And this, okay, so we move from the introduction. We I recall what is the k-contact geometry and eta Hamiltonians and eta Hamiltonian vector fields. And now we want to combine those both things together as before, but with some additional, in a slightly, I believe, more useful manner, or just a different manner. But the k-contact Lie system itself is the same, meaning it's just the triple that we have a k-contact form aim, we have a Lie system, and we have the Weissart-Guldberg Lie algebra, so denoted by Vx. And now we remember that this Weissart-Guldberg Lie algebra was spanned by the by the base of these decompositions, the vector fields that were included in the compositions. And now, if we want to define the k-contact Lie systems, we'll we'll make those base vector fields into the eta Hamiltonian vector fields, basically. And additionally, what is the main difference between my previous talk and now, additionally we can have something called the projectable k-contact Lie systems, meaning that every eta Hamiltonian k functions associated with the vector fields in our Lie algebra are the first integrals of the Reeb vector fields. And as an example of this definition, how we can combine those two things, we'll consider the manifold R5 equipped with such a coordinates. And now we can give such a two-contact form. So now we are imposing the two-contact form in such a manner. We're just giving out from the sky. And we can see that the Reeb vector fields that are associated with this are just the differential with respect to Z1 and the Z2. And now we can consider two vector fields on M in such a manner. So we have x0, x1, x2, x3, x4. And one can see that if we can make them eta Hamiltonian vector fields related to this two-contact form by just calculating the previous proposition, by using the previous proposition. And now I can see that we have eta Hamiltonian k functions of such a manner. And for the clarity, I will just say that this is indeed a Lie system, because if we find we have those 5 vector fields, we find those commutations, so we can see that they are closed under taking the commutations. And then we can define the two-contact Lie system, which will be related to the time-dependent vector field decomposed in such a manner. In such a manner that those functions are just arbitrary time-dependent functions, and those Weissart-Guldberg Lie algebra is spanned by those x1 to x5. I believe it should be x0 to x4, just the typo. What I want to underline is just in this case, we are dealing with the non-projective Lie system, meaning we can easily see that, for example, H4 is not a first integral of neither R1 or 2, neither the first or the second Reeb vector fields. And this example was a little bit artificial in the first, in this mean that we have to think about it and we can construct it from the scratch. And to get the non-projective k-contact Lie system. And the method that I will recall was just to produce the projective Lie systems. And I will recall this method because it also is useful. However, now we can find the non-projective one similar to this, not like previously, not from the sky, but just by the given problem. We can construct for the given system, we can make it non-projective one using this. Okay, so as a reference system, I will just give a system of differential equation on R5 on such a manner. So if we have x1, x2, x3, x4, and one can easily see that they are closed under the taking the commutations, and the non-vanishing commutation relations are given by there. So we have x1, x2 gives us x3, x1, x3 gives us the 2 of x4, and so on. So it is easily we can easily check that this system is indeed a Lie system. So we will try to make it a k-contact Lie system. And the first way how to do so and I will presented it before, is just noting that we are dealing with the locally transitive systems, meaning it's a diffeomorphic to automorphic systems.
Tomasz, locally automorphic, yeah, no, locally transitive.
Yeah,
there it wasn't changed, yeah.
I see. It should be automorphic. Yeah, not transitive. The locally automorphically system, meaning thank you. I didn't notice during the presentation. I have to correct this. But yeah, it should be our system, as we can see, is locally just the automorphically systems, because as we can look for the x1, x2, x3, x4, x5. In every point, it spans the tangent space of M, because we have x1, x2, x3, x4, x5. So it's a automorphically system. And what is very crucial for that if we have a locally automorphically systems, we can associate our Lie algebra. We can say that is a diffeomorphic to some Lie algebra of the Lie group G associated with V. Meaning, if we have this diffeomorphic, we can say that our vector fields are right invariant or left invariant vector fields. This is very useful because if we have automorphically systems, if we can say that those vector fields are right or left invariant, depends how we can say it, then we know that there is a family of the left invariant or just opposite invariant vector fields, in this case y1 to y5, which spans the Lie algebra V' isomorphic to V. So, and why this is important? Because they are symmetries of V, namely they commutes. And this is what we wanted before. And we will use it later if we want to make the more interesting contact Lie systems, but this property is very important and very useful because we are Lie symmetries from nothing almost.
Sorry, Tomasz, just one remark. It's V, no V. V is in Polish.
Okay, so force of habit, sorry. V, yes, exactly V. And if we can find those symmetries. I written them explicit them, and because they are linearly independent, because as we can see, this is the another thing that they are span. The dimensions are great with the tangent space of our M, meaning they are linearly independent, and we can find the dual forms to it. And why we are doing this? Because if we have a left, for example, I believe y was left. So if we have left invariant differential one forms, either they are invariant relative to the right invariant vector fields, namely the Lie derivative vanishes. And I will just quickly go back. So we are just this can be fulfilled trivially, and now we are just living with this term. So we can see that everything vanishes if this is a if this Lie derivative vanishes. So it is a eta Hamiltonian vector fields with eta Hamiltonian Ken functions, and we have eta Hamiltonian eta K-contact Lie systems. However, there are some additional comments how to obtain the eta, but I believe I covered it before. It's just I don't want to focus on this because this maybe not more interesting, and it was shown before.
Yes, Tomasz, yes, a little nuance. There is a 1/2 missing in these equations you wrote in d eta gamma. Okay.
Yeah, I believe.
Yeah, because it's the Cartan. They are Cartan equations. Mauer Cartan equations.
Yeah.
Summing twice of the English.
I thought that the sum ate it, but yeah, okay, yeah, because okay, sure. Thank you. Just about it should be 1/2, but once again, I just want to recall that what we are doing there is just that we are having the vector fields spanning the Lie. We said Goldberg Lie algebra. We said if they are spanning the tangent space of our M, we can say they are automorphic, so we can interpret it now as the left invariant vector fields. Then we can, or right, doesn't matter. Then we can find their symmetries, which are the opposite invariant vector fields. We are finding their duals, and we are obtaining, for example, we can construct the two contact structure using, for example, eta 4 and eta 5, using that the differentials of them does not vanish because, as previously, those structure constants does not vanish for these differentials. And once again, if we can combine those, we can easily check that those kernel of this eta is given by that d eta is given by the intersection of d eta 4 and d eta 5. And clearly they are of the constant rank and co-rank, and they do not intersect. So this is the two contact structure. And we can finally find its eta Hamiltonian K functions, verifying these conditions and obtaining such a eta Hamiltonian functions. And what I stopped before is that now we can see if I believe there is given y4 and y5 was just the differential of x4 and x5. So I can see that every...
Sorry, may I have a question?
Sure.
Just
sure.
out of curiosity, can you equip the space of eta Hamiltonian K functions with a Lie bracket?
Yes, you can. Actually, we can do it, and you can, because you were asking about the eta Hamiltonian functions, yes?
Yes, exactly.
Functions. I mean, yes, you can equip with the Lie bracket.
I mean, K functions.
K functions, yeah, sure. You can. I believe it was yes. You can. I don't remember from my head how it looks like, but you can. It is possible. It's a little bit different, but it works, and is of course related to the commutators of the corresponding eta Hamiltonian vector fields.
Yes, a remark. Thomas didn't add it in this work, but concerning the bracket of K Hamiltonians or eta Hamiltonians K functions, or concerning to the structure of eta, just the eta Hamiltonian K functions, the expression for the eta Hamiltonian vector fields, we found several operators and several morphisms that allow one to describe in a very nice way the properties of these eta Hamiltonian K functions. He didn't manage, but they are very elegant, they are very short written, and the way of writing this, the properties of these eta Hamiltonian vector fields and K functions is very, very nice. And much more of these expressions that are written in here, they look a little bit long and a little bit terrible. They can be described more easily. For example, when you have a K at eta Hamiltonian K function, there is a so-called Reeb associated Reeb vector field, okay? And this is exactly what it is written in the definition of the eta Hamiltonian vector fields along with the h mu e. So this expression that they are written in here for these eta Hamiltonian vector fields, they can be shortened by means of the so-called Reeb vector fields of eta Hamiltonian K function and other stuff like that. There is a nice theory, but I mean, it's the developments of this thing made by Thomas and ourselves is too long for just one talk to add it. But it should have been nice to comment on it a little bit. Thank you.
Yeah, sure. I mean, the way I presented it is more explicit, but it is completely sure that it can be using some additional terms, additional options to be shortened and make it much more clear, much more prettier. However, but this, I believe, is just the operations that condense those explicit formulas that I gave. So this is just the explicit way, but it can be, of course, shortened and make it much more, I believe, clear. It's for sure. Okay, so moving on, I want to underline that this is the way how we construct the projective Lie system, meaning those H1 to H5 is a first integral of our Reeb vector fields. And one can say it's not so interesting because we are doing something a little similar with the chi-symplectic theme, because we are only weaving that the contraction with our eta Hamiltonian vector fields with the eta is just the differential of our other functions. So it maybe can be it's not so interesting how to make for the projective, if we make the projective Lie systems. However, using the theorem that I was talking about with these decompositions, how to make the k-contact distribution, how to view the k-contact Lie system via the k-contact distributions, allows us to make maybe to construct another k-contact form, a little bit more interesting one. Meaning that we are doing all the same. We are finding that our Lie system is a Lie system, meaning that we find these commutation relations. If it's locally automorphic, we can find the symmetries of it really nicely. And now what we are doing, for example, we can see that in the simplest case, those commutation in this case, while the commutations of the Lie system of the Lie symmetries y1 and y2 is a distributional maximally non-integrable distribution maximally non-integrable distribution, meaning if one can see, it will be just for example a y1 commutator with y2, it would be something proportional to y3, I believe. Yeah, and what is important that we have a maximally non-integrable distributions. So the first part of our theorem is fulfilled. It have a commuting Lie symmetries, namely x3, x4, x5, because they are left and right invariant vector fields, and one can see that they commute x3, x4, x5, they commute between each other. So the next part is fulfilled, and for together one can see that they are spanning the tangent space of Tm. So we can see that we can construct the free contact form using the dual forms to this part. So now we are not taking the dual forms from the old symmetries. However, we are taking the dual forms from our distributional. It's like the dual to the distributional maximally non-integrable distribution given by the first two symmetries and our vector fields. And if one calculates it, I denoted it as a eta prime. So because once again, we can see what we are dealing with the same system. Before it was the projective one, because by the manner how we obtain the k-contact form. In our case, it was a two-contact form. And now we are changing the approach. We are using our theorem to find another set of differential one forms. We can calculate those differential of our one forms. And one can obtain, for now, that we have a free contact form using those free contact forms that are so-called dual to the vector field, for the vector fields, initial vector fields x3, x4, x5, and by some additional, one can verify that our theorem is true, meaning by hand we can see that the kernel of eta is this, the kernel of the eta is x3, x4, x5, and they do not intersect indeed. And moreover, because we took the dual forms, we make this x3, x4, x5 the Reeb vector fields of our k-contact structure. And now we can, once again, as before, verify the conditions. We can find this eta Hamiltonian k functions, and now they are different. So the x3 for the mu equals 3, 4, 5 is just because they are the Reeb vector fields. So this eta Hamiltonian k functions are just -1 multiplied by the base of our k, because okay, I didn't add this, but this mu, F3, F4, F5, etc. is just the base of the F3 because we have free contact form. And the crucial part, the most important one, that we have two different eta Hamiltonian current functions, and they are clearly not the first integrals of the all Reeb vector fields. One can simply calculate, for example, x3 acting on H2 prime is just a minus I5, it's not zero. So as we can see now, using this theorem, we can construct not only projective Lie systems, but only non-projective ones. So, and this, we can see that this procedure is very, very easy. It's like if we have a proper systems, those steps are almost the same as before. And what is really interesting, that if we have more, because in this case we have 5 vector fields, but if we have more, for example 8 or so on, we can, by checking if we are, what is this maximally non-integrable distribution in our case, we can make it larger, smaller, between, it depends on the commutation relations. We can associate different contact forms, for in this case 3, but in examples, what we in our paper with Javier and Xavi we are doing, we are making checking the examples from the PhD of Arturo Ramos, and there are a lot of examples that can be done in an automatic even way, and we can find different eta Hamiltonian, different K contact forms with different eta Hamiltonian K functions, and we can make them the different eta Hamiltonian vector fields. So this was lacking before, and I believe it is worth noting that this theorem is really useful and really powerful. And we'll use it also later, meaning this later for the PDE systems. And this is the brand new. I finished what is the K contact systems before, because before we are dealing with the ordinary differential equations. And our goal as a K contact, because K contact geometry itself aims for the systems of the partial differential equations. So I will briefly introduce what does it mean to be a PDE system. The PDE system. So as a definition, I provided what does it mean to be a time-dependent K vector field, and this is definition. I can explain it, but once again, I refer to the previous talk, and I believe it was said many times. I want to think about the time-dependent K vector field as a regular K vector field. So once again, it can be viewed as a tuple of K vector fields, but now each one of them is time dependent. So it's just the combination of those two different notions said before. And this is definition what can be said precisely, but I believe it's more natural way of thinking, because previously, if we are dealing with the K vector fields, we have those gamma, those integral sections, because it could be more than one, but for the clarity, it's just the one particular integral section. It was the differential or with respect of the parameter T alpha, because our T it's not from R, it's not only one T, it's from Rk. Now this elements does not only depend on the gamma itself, but also on this whole parameter T. So now we have a time-dependent parameters, not only time-independent or T-independent. So once again I said the details are previous. I recommend to see the previous talks about what is the time-dependent K vector field, but I want you to think as a tuple of the K vector fields, each one of them being the time-dependent vector field. And using these notations of the time-dependent K vector fields, one can define what is the PDE systems, meaning we want now have a system of the partial differential equations with the superposition rule, which is just the superposition rule as we know. So once again, we want to express our, in this case, gamma as a function of the particular solutions and some constants. And and the system has such a superposition rule if its corresponding time-dependent K vector field can be decomposed in such a manner. So this is very similar as before. Before we just have one specific we have one specific time-dependent vector field for a systems. Now, because we are dealing with the k vector fields, we have this index alpha. So each one of them has to be decomposed using such time-dependent vector fields, and which each one of those vector fields that only depends on the point on the manifold, those vector fields has to span the r-dimensional real Lie algebra of vector fields V, meaning similar as before the Weiswort-Gulbert Lie algebra. And the additional thing that has to be fulfilled, which wasn't before, it has to be that our time-dependent vector field X has to be integrable, meaning every element of those X, meaning every element of our tuple has to commute with each other. So xi with xj, where I and j comes from 1 to k, has to be, the commutator has to be 0. And if this is fulfilled, then we have a PDE. We can say that we are dealing with the PDE systems. And as an example, I will just give you a special case of the system of partial differential equations as a particular case of so-called Wess-Zuminow-Novikov-Witten systems. And in this case, it's just given that if we have a psi from our manifold and differential of our psi will be an integral section of our system, of our time-dependent K vector field, and they have this form, meaning that the partial derivative of our M element with respect with Ti is just the sum of some time-dependent coefficients times its elements times the element of Lie algebra G, and additionally those elements spans the basis. And we have the same, but now we change the place of psi. So now we have the action of the m beta psi f, and there we have the in other way around. And then we can one can see that those indexes goes from I to minus I, meaning we have in this case 2R differential equation, partial differential equations, and we can like separate it, making that we can decompose it into two parts. Meaning, for this case, we'll choose the basis for the with the left invariant vector fields and the right invariant vector fields, just to reread this system of partial differential equations in such a manner, because this is the really close one what we wanted to have for our system to be a PDE system. So writing the system in such a manner, one can see that this system is associated with the 2k vector field, meaning the first elements. So we are, because the indexes goes from the minus n to plus n. So first n elements from minus 1 n to minus 1 are the left are decomposed using the left invariant vector fields, and the rest is using the right invariant vector fields. And why we did it? Because now it is really it's trivial to see that the left and right invariant vector fields span a finite-dimensional Lie algebra together, because they commute between each other, and if we assume that they do not intersect, they span the Lie algebra isomorphic to the direct sum of our initial Lie algebras. So we can see, so we have finite-dimensional Lie algebra, and additionally we have to impose the integrability conditions, meaning this has to be fulfilled. So with some additional remarks, for example, that those coefficients has to, so the first n coefficients has to be depends only for the first elements of T, and the rest coefficients has to be depends on T, and both systems are integrable. Then our Wess-Zuminow-Novikov-Witten system is a PDE system. And this is, and as a summary, the why I talk about it, because we can now see that if we have, for example, the k-contact Lie system, we can make every vector field related that spans the Lie algebra, the Sod-Gulbert Lie algebra, into the eta Hamiltonian vector field. And the same we want to do is with those elements, because now, so we have a PDE systems. We know that this is the PDE systems if we can decompose it in such a manner. And now, if it's all fulfilled, we can make those left invariant and right invariant vector fields, or just the vector fields that are used in the compositions as the eta Hamiltonian vector fields. And I didn't write it in explicit, but we, for example, show that if we have a k-contact eta or time-dependent k vector field, and each one of these elements fulfills in tuple is a eta Hamiltonian vector fields, then the time-dependent k-contact vector field itself also is eta Hamiltonian. So we can find, for example, its Hamiltonian function using the fact that this theorem can be proved that this can be that if each one of them is a eta Hamiltonian vector field, then the whole k vector, 2k vector field in this case is a eta Hamiltonian vector field. So we can use the previous things, the previous results to analyze the PDE systems, and this is our goal for now. And I believe this is the state of art for now. And I'm not don't sure how much time
You have crossed the time in 15 minutes.
Oh my God! You could tell me so I will speed up because I don't have watch with.
Okay, we always cross the time. So if someone has to leave, he can leave.
Okay,
the official time. If he has the obligations to do so, yeah. So don't worry, it's okay, it's okay.
Okay, so that's all what I wanted to say.
Thank you, Thomas. Is there any comment, remark, question?
Can you hear me?
Yes, I do hear you.
Okay. The other day the mic didn't work. Can you go back to the definition of the k-contact Lie system, please?
Down. K-contact Lie system. Yes, up.
Okay, it should be.
This is the projectable, right?
Yes.
Okay, yes. So the question is, how is I don't know if I misunderstood, but how is the k-contact form relevant for X to be a k-contact Lie system? What I mean is, if X defines a k-contact Lie system for certain k-contact form, is it a k-contact Lie system for another choice of k-contact form that defines the same contact distribution or k-contact distribution?
I'm not sure that I get it. Could you repeat? Because I think
yes,
I know. But...
I try to
maybe I will tell because it's we cannot hear Ruben.
So
state what you said if you want, because we cannot hear you. Oh, it's okay now. Please repeat. Talk.
You cannot hear me?
Now we can. Now it's good.
Okay. How important is the dependence on the k-contact form for a Lie system to be a k-contact Lie system? So if a Lie system defines a k-contact Lie system for certain k-contact form, does it define a k-contact Lie system for another choice of k-contact form that defines the same distribution? I don't know.
I believe in this
myself.
I believe. I mean, I believe if I understood it correctly. something is sometimes.
Okay, go ahead, Thomas. Don't worry, he has finished.
Okay, so I believe, if I understood correctly, yes, if we have because in this case, what we there. For example, in this projectable, because yes, this example may be good to be seen. Meaning, in this case, we have just the list. We found the Sodbull-Berkeley algebra. We found that they are close under taking the Lie systems, and they are. We can find in this even case we find two different K-contact forms that define two different. One was a projectable one, different. The one different. So one was the projectable one was not, and one can see that, for example, so then we have two different K-contact forms, and we obtain two different K-contact distributions. So I believe if you can find one, I believe it's only associated with the one. Then I mean, if I understood it correctly.
Thomas, you are answering another question, not the one Ruben did. I will resume. The thing is, the answer is yes. If you have a K-contact Lie system and you have an eta form, okay, this eta form defines a contact distribution. Okay.
Yes.
So any other K-contact form defining the same K-contact distribution will turn your initial K-contact Lie system into a K-contact Lie system too. Why?
Okay. So it wasn't about two different, but if they coincide. Okay. I now understand. Yes. So yes, of course. Of course.
So I mean, if if you have a K-contact Lie system, that means that a Bézier-Goulbert algebra of the Lie system consists of symmetries of the kernel of the eta. If you have another eta and defines the same kernel, it will always be again a K-contact Lie system with respect with the new eta. This is always the same. But the thing that it is projectable, it depends on the eta, because for every different eta, for different etas having the same kernel, okay, you can define different families of Reeb vector fields, okay? Because being a Reeb vector field or locally, well, a Reeb vector field of the eta, it depends on the eta you are choosing. So if a certain K-contact Lie system is projectable, it means that it is invariant with respect with the Reeb vector fields. If you define different etas with respect with the same K-contact distribution, different etas may have different Reeb vector fields. So your initial K-contact Lie system can be invariant with respect with the Reeb vector fields of one eta, and it will not necessarily be invariant with respect to the other. So summing up, if you have a K-contact Lie system, in reality, it's a K-contact Lie system with respect with the curve of eta. But the fact that it is, and eta is something superfluous in a certain sense. But being projectable is something that depends straightforwardly on the chosen eta. So I hope that answers your question.
Yeah. This clarifies it.
Okay,
so
thank you.
I guess the interesting. Okay, thanks. Yeah, I guess the interesting aspect is for finding a projectable. Am I wrong here?
Could you
Did you
repeat?
hear me?
Because...
Maybe. Okay. Yes. My internet is a bit unstable. So I guess the interesting thing is to find a projectable K-contact Lie system, right?
In the other manner, not the non-projectable ones, because if we have a projectable, then all the eta Hamiltonians are the first integrals of Reeb vector fields, and we can say that we are left in the projectable one case in only these conditions here. So it's really similar, like for the symplectic case. And the interesting part is that we want this part. We want that we have such a K-contact form that its eta Hamiltonian K functions for the eta Hamiltonian vector field, it's not like it's not the projective ones, because the names comes from that we can project it from the symplectic case, but we won't have this part, so it has to be a little bit distinguished. So the art is to make the list system not projectable. I mean, we can do both, but I believe the non-projectable one is a little bit more distinguishing one from the K symplectic case.
Okay, thank you.
Yes, a part of comments we can finish because a little bit late. When you have a K-contact structure, and the K-contact structure is corientable, you can extend the K-contact structure to a K-symplectic one in a manifold of larger dimension in many cases. In those cases, the initial system can be mapped into a K-symplectic system up when these conditions are satisfied. And the thing is, sometimes the properties of the initial can be reflected in this one, but the relation is not a good one. When the system is a contactless system, this works perfectly. You can go to a simplex and so on. So, and when it's projectable, your K-contactless system projects onto a K-symplectic system in a manifold of lower dimension. Okay, so you can study that, and the K-contactless system is an extension, which can be described by means of a reconstruction problem. So you can go down when it's projectable, and under certain conditions you can go up to a K-symplectic system. Yeah, but these are constructions that work sometimes. This is one thing. The other thing, another comment is that many of the techniques, reduction and things you have been doing, they can be applied to these K-contactless systems. It's not be done in general. There is a K-contact reduction work by Bartosz, Xavi, Silvia, and me, and can be applied to this. But there are certain questions still to be described, because it's about momentum match. You can do it with isotropic manifolds and things like that. It's an open problem that is related to what you have done for them. Also, the description about K-contact Hamiltonian vector fields and functions Tomasz left in this talk lead to describe dissipative K-contact Hamiltonian vector fields. And it turns out that there is a relation very similar to the one done by Assier in his PhD dissertation. And many of the things that Assier did can be extended to this K-contactless system, all the theory with the dissipation, okay? Taking into account that the relation between K-contact, K-symplectic, contact and symplectic things that can be done for contactless system, in this case are not straightforward and cannot be applied always. And also, these are things related to field theory. So you can expect that the result you obtained can be extended to some extent, but the result will be technically much more complicated, okay? But the thing is that we already have lots of examples where this can be applied. So it's a possible field of study if you want. And that's all I have to say. Any other last comment? No, so we can finish. Thank you for attending. This has taken much longer than usual. If sometime this happens again, please, I know the some of you can have lectures, so I understand that you will leave. Thank you very much. Thank you, Tomasz, for giving my talk. It was very well done. Thank you.
Thank you.